All right, can everyone see my screen? Okay, thanks, Greg. All right, so stack should have been pretty simple for everyone to understand, just because it's something we went over in the sprint kickoff lecture. And so, and then queue is pretty much the same. It just acts a little bit differently than stack. You just have to change a couple of things. So in order to get this to work, let's take a look at the test real quick. So the first test, there was a question about the tests in the review that I saw, and I responded to that right away in the sprint review. So the first test will usually just check the methods that are on the class itself. So it's just going to ask if it has a remove, or it has a remove, an add, remove, and a size method. So they've got to be the same as these strings here, because that's what we're doing with the test. We're making sure that these, the stack that we create before each it in this code, before each function is going to get called, and it's going to create a new stack based on your stack that you have in this file. Okay, so that's how before each works. So stack equals new stack. So that's why we can say, let's look at the prototypes on stack and see if it has a property called add, remove, and size. So that's what that's doing. So if you have a typo in any of those, you're going to fail this first test. So let's just make sure that we have our constructor set up. Okay, and let's make sure we have add, remove, whoa, we don't want to do that, and size. Okay, now add is simply going to add a value to our stack. So remember, as we have our stack, right, let's start at the bottom here. So just drawing our little stack, pretty simple concept to understand. Our add function is going to take some sort of value and it's going to place it on top of the stack, okay? And then remove is just going to simply look at this stack and pop that value off. So remove comes and pops the value off the stack, and then size simply just counts the number of items in the stack, okay? So that is pretty straightforward, just because it's a pretty conceptually less challenging data structure to think about. So first off, we need some sort of storage object on our constructor. So what you do, obviously, when we remember just the syntax, when we're creating our constructor functions, our classes, we're using the keyword this to point to the object itself. So point to this stack object and give us a property to set on that. And so what I like to do with stacks is just conceptualize it as an array, because it's super easy to work with arrays in JavaScript. And that's something that you guys should be pretty comfortable with by now, is kind of working with arrays, at least being able to add things to them, remove things from them, traverse them, update data inside of them, things like that. So very, very common pattern there. So we take a value that comes into add. Okay, so let's look at our test for add. Okay, so size should be pretty easy. Let's just do that real quick. So all we need to do is return this .storage.size or .length, right? And that should return out the value of this storage. So, and that's probably all we need to do for size, and then 0 should be for a new stack. Okay, so yeah, so stack.size should be 0 at this point. And is that the only test that uses size? Okay, so we actually will be using size after we use the other methods. So these tests are going to not run all the way through. I could probably run a test and see what it looks like right now. I'll probably pass the first one and then maybe that second one. So npm test-stack. Okay, so we've got should not error when attempting to remove an item, which is funny because we're not removing anything yet. But yeah, we passed the first one, and then yeah, so we've got to finish, we've got to complete everything else that, in order for it to continue, because size is going to do, it's going to look for, yeah, so it's going to run this one, and it's going to, yeah, so we need to make sure that we have the other methods built. I'm going to just maximize that. Okay, so all we do for this is simply this.storage.push, because the value that comes through should simply be pushed into the stack, one by one. So if we treat this array as our stack, as we push a value in, value is going to come in. So the first, value is going to be there, value every time it's called, right? So this is kind of how we're treating our stack. So value, value, and then when we call remove, it's going to simply remove that last item. So for that, all we need to do is pop the item off. So this.storage.pop. Okay. And that's going to pop. Oh, I need to actually return that, because otherwise it's just going to, the evaluation of pop if it works the way I think it will just simply return the length if you don't return the value popped off the top of the stack. So let's see where we're at with stack. Whoops. And we can move forward from there. So we have should return a size. Do I have a typo anywhere? So we should return size 0 for a new stack. Should return size of 10 after adding 10 items. So, well, I have a typo here. So maybe that's where the typo was. So, not really sure what exactly I'm doing wrong here, but this was exactly how I just did this. So let's see. So should return a size 0 for a new stack. So add remove size.
Hey Ryan, should size be in the constructor?
Size actually should not be in the constructor, but I just remembered. So size is actually a property. So if you look at our tests, size is actually going to be defined as a prototype. So
which one are you failing?
A prototype property, but we actually need size to be a getter, because that's what the instructions are treating it as, or that's what the tests are treating it as. So if you look right here, it says should have the methods add, remove, and a getter for the property size. And I probably corrected a few of you on this, but there are two properties or two keyword helpers that help us specify what our functions are. And so, oh, Jake, thanks. I just saw your thing, so we're on the same page.
Hey, Ryan.
So, yes.
For your remove, what if your stack is already empty?
So you're saying, so if this dot storage dot size, well, I'd say, okay, so what if I did this? So I call size, so if, size, because I can call it'd be this dot size, right? So this dot size equals 0, because that's just going to return the length, then we could probably just return, right?
I would say return 0.
Return 0 itself?
Yep.
Sure, that works. And then, yeah, because then that'll do the case, but yep, yeah, so that should work. Now let's see. So, and then, yeah, our getter, we needed a getter here. Just be looking for gotchas like this in the readmes. It says a getter. Anytime you hear the word getter or setter, it's referring to calling this function, as a specific getter. So it's sort of like typecasting the function itself and saying, hey, this type of function is a getter. But now it says should not error when attempting to remove an item from an empty stack. So I wonder right now if I can just do this real quick. because it shouldn't error, and it was giving us an error on that line right there. I think pop has a failsafe in it, yeah. So that should have been a good failsafe, but we can move forward without that. So it really is that simple. So yeah, there is that failsafe that Ty was suggesting we put in here, and that works really, really well. But with the tests, I'd have to go back and see it all before. I have to go back and look through all the tests to make sure that we're in the right spot for that, to see exactly what was going on with remove. My guess is that, oh, you know what? I think I could have done this and just said, the get method over this dot size, so that way it recognizes it the same way the tests do. Let's double check that. So, and I'm going to say if it's less than 1, just so if there's like, I don't know, array lengths cannot be negative values, right? So I guess we're safe if we do 0. Yeah, so still this, for whatever reason, is tripping me up. So I'll have to go back and research and figure out a better failsafe on that. But yeah, for the tests, it should just pass if you just simply, if you build this stack as like sort of a very simple basic understanding of a stack. So awesome. So I don't feel like there's tons more to discover here with stacks, and we can move on to queues. So let me just start this one from scratch here. And so yeah, with a queue, it's basically the same thing. So you have your constructor that basically gives us our storage object. Okay. And then we have our, what are the methods called? We got to look for them. It's enqueue and dequeue, right? So should have enqueue, dequeue, and size. So I'm just going to take those right out of the tests and turn them into methods. Whoa. Okay. So enqueue is going to take some sort of value the same way that add does, and it's going to just it's going to add it to the beginning of the queue. So we want to what here? We want to unshift the value, right? And then dequeue is going to do the return this dot storage dot pop. So instead of pushing to the front, we're gonna unshift. So we're gonna push it to the back of the queue, right? So
Push puts it to the back, and shift puts it to the front.
Right. That's exactly what it. Oh,
Yeah.
Shift or unshift? Do you want to shift here?
Unshift. Sorry.
Okay. Just making sure that I can fly through these, and then we simply want to return this dot storage dot length. Okay. So once again, with our visualization of how this queue is to work, we want to let's draw it out. I'm going to use gray. So we have our queue of items that come in, right? So as we unshift, so let's say this is the basically. So here we would have like an array that goes 1, 2, 3, 4, 5, right? So 1, 2, 3, 4, and so on. So if we're popping, then this is going to be what comes in as the first in line of the queue. So when we pop, we want just this to behave the same way that it behaved. It comes out of the front. So, but as we unshift, our value comes into the beginning of the array, so it's going to come in down here and put the value into the queue. So that way we sort of treat this array as, putting values in backwards, right? So, and then the length is simply going to count the nodes inside of the storage and then return them out, or return out the length. So let me go back, and let's see if these, essentially do the same thing. There we go. Oh, trailing spaces on 10, 4. 10-4, good buddy. Okay, so that should satisfy all the tests for your queue. All right, so stacks and queues. Let the questions come in. You can post them in Slack. You can ask me. I guess we can ask. I can ask you specific questions. So, what is an acronym to describe the behavior of the stack? Acronym meaning like SCUBA means self-contained underwater breathing apparatus. How do you like? How would you? What is the? So the acronym would be, okay, so last in is the first out, yes. Another way to describe it would be the first in, last out, right? Because it's the first item in is the last item out. But yeah, last in, Antonio got it. So stacks are last item into the storage, the first item out. And then what about queues? What's an acronym to describe queues? And what does FIFO mean? What does FIFO? I guess we can understand it from. So first in is first out, right? So it's just like you go to the deli, and I like food examples. So you go to the deli, you get your ticket, and you stand in line and you wait. You're going to be the first in line to get your food if everything works at the restaurant or at the deli itself. Okay. So first in, first out, last in, first out. Those are our ways to describe those. So pretty awesome, like high-level data structures, and they're really, really powerful. I failed to mention, I think, when I was going over this, is that queue is used in the event loop in JavaScript. So like everything sort of gets, when you build your stack is your compilation time, and it goes through and it just adds items to the stack. And then once it's ready to blow off that stack, it just goes and pops everything off the top, and your program operates and runs. With a queue, you have an event loop in JavaScript that sort of takes advantage of the space. So since JavaScript is non-blocking, you can write non-blocking functions that one is executing, but one could be executing behind it as well. And then we'll get into this idea of asynchronous programming, where a function you can write in your program is actually, you're going to specify that it's going to fire at a specific place in time, depending on the type of data that you get back from like a server. So when we get into server-side programming, we do a lot of asynchronous programming, where you're using promises saying, this thing isn't defined yet, but when it is defined, then fire this function. So JavaScript's really, that's one of its major strengths, is this asynchronous stuff that we'll get into further on when we get into Node. And I think we'd even touch on it in some of the React stuff. Okay, so let's move on to linked lists. We had some feedback that said we had a little bit of trouble going through this. And in the sake of time, I'm not going to try and craft out a linked list for everybody right now. I'm just going to use a solution that was provided beforehand. So with a linked list, remember, let's visualize this with our little code visualizer, our annotator. And so with our linked list, remember we have these nodes, and they're separated as some sort of data here. So data, and then a reference, right? And then that reference points to the data of the next node. And so if you want to make sure that you have access to, so new data, reference, a pointer, right? Okay. So, and then if you want to update this data reference, and so if this pointer doesn't point to anything, then it's going to be what? So if this is the front, if this is the top of our linked list, and this pointer doesn't have a value to point to, what type of node is that going to be? Null. What's null going to represent? So if this points to null, sorry, I should have asked this more clearly. If this points to null, and this is the top of our queue, should be the head, right? Maybe not the header, but because header will could throw you off in a different context later on. But yeah, the head. So this would become our head in this case for this linked list. Okay, and then these other ones would just be nodes in the linked list. So if you remove if you remove a node from the linked list, then you essentially break this chain and you point the reference to the next node in the chain. Okay, and then if you add things in here, so if there's nothing pointing here, then what is this going to be in our linked list? This should become, if this one's the head, this one should be tail, correct. So that's kind of how a linked list works. So the next node that comes in, this node stops being the tail. We get a reference pointer and the node data value, okay? So that's kind of how you visualize this. So the new data in becomes that or does it become the head? Can somebody correct me on that if I'm wrong? So the new data in becomes either the head or the tail.
If there's no head and there's no tail, then it becomes both the head and the tail.
That's true. So now what about if we're using our add to tail, we're adding the items to our tail. So that's right. Cool. So I wasn't steering us off the course by saying by adding items to our linked list, we're going to be adding them to the tail of the linked list. So the next item that comes in then points to the new item, and then that gets the tail, and then that other item becomes the head. So yes, if our linked list is empty, then yes, the node that comes in is going to be the head and the tail. So it kind of gets a special reference. So awesome. That's linked lists are pretty powerful as they sort of piggyback off of arrays and make them a little bit more optimized for, essentially you can think of a linked list, as a type of array, but instead of trying to figure out where you're at in the array and just add things in, you're sort of adding them to the head and tail. And then you have like a reference point that points to the next value. So think of a linked list like an array where you have like an index key value pair, but then you have a pointer on that node, on that, say that index was at 4, that pointer would tell you what the next value is in that array. So they're basically taking arrays and making them super arrays in JavaScript. But obviously linked lists existed before the JavaScript language. This is an old paradigm. This is an old data structure, but that's just kind of how you go through it. And yeah, Alan, I can actually post this stuff in the console right away, and I can show you how that works as we increment the linked list. So let me just walk through this real quick. So the first thing we need to look at is every single time we add a tail, we create a new node and then assign the value of that node that comes into the tail. So if you look at our tests, let's see, that one. So if you look at our tests with our methods, we should have an add to tail, remove head, and then contains. Okay, so with the tail value, when the new node is added, so it's going to say list.add to tail, add 1 to that tail. So then basically you're saying the value that comes in gets assigned to the value that's going to be on this new node object. Okay, so let's see how it creates this. Okay, so before each, create a new linked list and then perform these operations on it. So right here, this block is what we're looking at right here. And then we're going to make sure that it also keeps the same head after adding the nodes. So we need to make sure that the head is contained, that we have a reference to it. And then we also need to, that's contains, look, okay, so list.head.value to be 1, 1, okay. Cool. So that way we make sure that as we're updating the head and and the tail as necessary. All right. So as we come through here, we create a new node on this object. Value gets assigned to value, and then initially we're just going to set a placeholder on next, and then do some checking to see if there is a next value. And then if there is a next value, then we're going to assign it something. Or if there isn't a next value, if there isn't a next value, then we're going to assign it something. Otherwise, we're going to worry more about the tail on this list. Okay. So right here is where we check this.head equals null. So if it is null, then we're going to assign the head to the new node itself. Okay. So this.head equals new node, and this.tail equals new node as well. And then we're done at that case. So we're done at that case. So if they equal that, then we move forward. So now every time we come in, we should have a node. Let's say we called this once, add to tail, and we added this new node and then to the head, and then the new node becomes the tail as well. So let me just draw that out because it sounds confusing. So the first time we call this, we're going to add a value. and then our linked list is gonna look just like this with data, and then so that would be the data would be, you know, whatever our next or our value is, and then the next would be our next, right? So now it's saying, okay, so if we come to this linked list and this dot head equals null, then assign it the head. So this becomes the head, and then it also becomes the tail because we have nothing else to reference it. So that's what this is doing right here. It's checking if that head is defined, and if there is something there, then just assign it to that new node coming in. Okay, so it becomes our first item in the list, and then we don't need to worry about anything. Okay. So now, in the case that, and I'll leave this up here, in the case, oh, can't scroll without ruining my beautiful illustration. So in the case that there is a value assigned to, you know, so if head is defined, okay, so now we need to check if our next node is actually defined in the value. Okay, so that way we can kind of keep a reference to everything and walk down the chain as necessary. So if this dot head dot next equals new node, then and this dot tail, so sorry, if this dot head dot next equals null, then assign it to the new node coming in. Okay, so in this first case, this is also going to be the new node, right? And it's also going to be the tail. So that's why there's only one node here. Okay, and then the second time it happens, it's going to be like, oh, there's already a head, so let's look at next and say this dot head dot next equals null. So now we can add a new item, and we're going to set it equal to, so the next is going to be pointed to the new node. So let's annotate this. So next, right, is going to be, so the next of this new node coming in is going to be pointing to next. It's going to be pointing to the new node itself. Okay, so that new node that comes in, and then the tail is going to be assigned, you know, now it's not going to be here, it's going to be here pointing to that new node as well. Okay, and then we would return. So now every single time that happens, we just want it to continue that same behavior, but this time it's checking for both of these null cases, and then it's like, okay, those don't get met, so now we come down and we can just simply add every single time next comes in. We can add it there, and then the new node data continues to get pointed. Okay, so that's where linked lists are you know, good. You just insert them right there, just that same way. And Alon wanted us to show how this works in the console, or kind of use our linked list. And so let's see if I can get this up and running. And get a new Chrome browser over here. Can you guys all see my Chrome browser now? Thank you. All right, so I'm gonna just call that, just create that class, and I'm just gonna say, let's see how our tests do it so that we can do it the same way they do it. So it says list.add-to-tail and just simply pushes the value, but we have to create our new list. So let's say list, let's say this. So const list equals new linked list, just like on this line here, but we're going to do that in our console. Let's say const. Give you a good idea of how this is working. And then we'll just say list.add-to-tail. And then we're going to push it a value of 1. Okay, and let's check out our list. Oh, not that. Okay, so now you can see our first time we called this, we just called it with 1 value. Our head, you can see, is pointing to null, and our tail is also actually pointing to null at this point because there's nothing behind it. Okay, but we both have our first time we called this, the node that came in was that new node. Right, was this, sorry. So the first time it came in was this new node, and that got assigned the head and the tail at the same time because nothing was there. So this condition actually hit right here, and it created a new head and a new tail assigned to the new node that came in, right? Okay, so now let's do it again. This time add the value 2. All right, and we'll look at our list. So now you can see we have 2 objects in our linked list. One is at the head and the other is at the tail. So if we look at the head, next should be null, okay? And then the value should be 2. And then our tail should still be the same because there's nothing, well, there should be, oh yeah, okay, so here it is. So next is this, so look at this, cool. Awesome, this is working exactly how I expected it to, which makes me happy. So let me get the annotator. Okay. Sorry about the, okay. So look what happened here to the second time we called this, our next object, our next, pointer here became this node, okay? So it became this whole entire thing here. So that's now creating that paradigm where we have, our head has the value of, so next is null on our head right now, and then our value equals 1, okay? And then right here, you can see that we have a pointer, so a reference that is linking up in the linked list between our, so this tail right here, this is the tail, right? So labeling. So you can see now that it's pointing to this value of 2 is, pointing to the next value. Easier to see it going down. Yeah, that's probably true, not left to right. So yeah, we can add a couple more and check it out. So let's call it again and add 3 and see what happens to everything. So you can see now our tail has the value of 3. Okay, so 2 is still in this chain somewhere, right? Now, so 2, now our list sort of looks like 2, 1, 2, and 3, but our tail, we're really just keeping track of our head and our tail. But if you look in here, you can see the next value is sort of nesting these objects and pointing to them and keeping reference to them. So now you can see all the way down our chain, we have our head at 1, our middle value is 2, and then our tail is 3. That's sort of what this, let me draw again. This is all, this prototype chain is representing this. There we go. So this prototype chain is representing this idea that 1 would be the head, 2 is the middle, and 3 is the value. Okay? So, and then our tail, so yeah, this is our tail right here. Tail, it's hard to write with this thing. And then this is our head. Pretty good visualization there. Okay, so I'm going to clear that. So that is the adding to the tail function method that we built on our linked list. Now let's look at removing the head. Okay, so as we call remove head, should remove head when removed is invoked. Okay, so list.addToTail1, list.addToTail 2, and then expect list.add to be 1, and then list.remove head, expect list.head.value to be 2. So in our list, that's sort of a really good way to represent how we want to remove that data from the list, is to simply just take the head off of the data. So if we need to visualize that in this, well, we can just look at the code real quick. So if this .head is null, then we don't have anything to remove. If this .head.next is null, then the head becomes that actual head, and then we need to just reset it. Oh, whoops. We need to reset the head and the null, or head is null and then the tail as null as well. So we just reset the head, right? If it's just if there is nothing else there, we just reset that head and then we're done. We return head.value. Okay, so we just return null out of this is essentially what I believe would happen. And then the same thing with, okay, so now if those two conditions are met, where, if there is no chain and if there is no head, then it's going to come down and it's just going to assign value. It's going to say, value equals this dot head dot value, and then this dot head equals this dot head dot next, and just return that value. So that way we just shift off that head, and then we just say our head becomes this next object in the prototype chain, in the linked list chain. Okay? So pretty simple here. And then for contains, this is a little bit more involved because we're actually, the best solution for this is to simply use recursion. And when I say simply use recursion, that's not something that's easy. So what we need to do is just basically loop through our linked list and just say, hey, if there is a value at at the next value. So if there is something defined at node.next, so anytime there is, then it's going to actually continue to loop. Otherwise, it's going to return false, and it's going to break out of that recursion and then get us the new head. So that way we can see, what is. Oh, but we're also, so with contains, we're checking to see if the object actually exists in there. So we have two cases here that'll break us out of our recursive loop. So we create this function and we say, so node is going to be what gets passed to this function. Okay, so the node that we're looking at. And so that in this case, the first time we look at it, we're going to start at the head, and then it's going to go down. It's going to see if there is a next value. So if this actually has a value that's not being pointed to anything, then and if that value actually equals the value coming in, then we're going to return that. Otherwise, we're going to look and see if the next value is not defined, then we're going to return false to break us out of this recursive loop. And then we just move forward until we find value where it equals the node's value on that node object. So, and I can show you how this all works and sort of conceptualize it once again. So let's move into our console. See where that's at. Not there. Oh, I deleted it. That's fine, because I can do this. Always make a new one. Okay, and then we'll take our linked list, put it in Chrome. And yeah, I'm using the latest up-to-date version of Chrome, so whatever features they have built into the browser I get. I think there was a question about if it's if I can use ES8 in here. I don't know much about ES8. I've just seen that they barely released it like a month ago, and so it's very brand new. So we're just trying to get caught up with ES6 here. So now we can say const list equals new. Come on. That one. Okay, and then we can say list.add to tail again. We're going to go 1. Okay, list.add to tail as well. 2. It doesn't matter what values we put there because you're going to store them in a new piece in that list. And then if I do list.contains and say 1, should we get true? And then say 12 should give us false. So that's how you do your contains. It's done recursively. And then if we want to remove head, we can say, we can just simply call this or we can just call list.remove head, and then we'll log the list. So let's look at the list now. Whoops, done that a couple times. So we'll call list now, and we'll look and we'll see we have a head and a tail. Head is going to be, assigned what the next value is, and the tail is, 3. So 1 should be at head's, value, and then our tail should be at 3. Okay. Now, if we do list.remove head, simply call that. So it popped off and it gave us the value that came off of the head. And if I log the list, we should have value at 3, value at 3. So if I call that again, dot remove head, now our list should be just empty, null and null. Okay, so conceptually, that's how a linked list works. I know it gave a lot of people some heartache to sort of conceptualize this through code, but I promise these things get easier and easier as you continue to go on. as you build this stuff out and you kind of figure out how it works, and it just takes time to study it. We don't expect everybody to be able to craft this from scratch right now. That's not a requirement for you to be able to do this at this point. Maybe after graduation, you go back and you review this sprint specifically, and you try and memorize exactly what a basic linked list should be doing, and try and build it from scratch, and reference things, and then try and do it to where you can just do it over and over again. To be honest, right now, I don't think that I could just jump in and build this from scratch right away. I know that I could do it. It would take me a while to remember how to do all of these things just right off the bat. So there isn't a point in your career where it's like, oh, I can build a linked list from scratch just in minutes. There could be a point where you get there. But like if I'm preparing for a job interview, I'll review this stuff to know the concepts, and then I'll be able to at least remember the steps, So when I get to my add to tail function, I have a value that comes in, and that's going to check if the head and the next are defined, and if they aren't, then assign it value, and then otherwise just move on and assign the next value. So Ty, how many linked lists have you, built from scratch in your life? As a graduate, is Ty still here? Maybe he's not. Okay, well, that's fine. So now we're going to move into looking at hash tables. And this is one that, once again, it's going to be similar to linked lists, that it's just going to take a lot of time to understand what's going on with hash tables, okay? So don't feel bad if you don't understand this now, or if you only got through stack and queue, you're just fine with your partnership. If you got all the way through hash table, you're definitely doing great. And my intuition is that one or both of you had seen this stuff before, because I didn't even give you any like examples or go over hash tables with you guys. So if you were able to implement it, consider yourself that you got the extra credit on this assignment to get the hash table done. But I want to make sure we understand at least the high-level principles of a hash table. So a hash table, if we're to look it up, and I'm not going to be able to give you tons of like examples of running it in the console because there's a ton of moving parts here. As you can see at the very top of your hash tables assignment, you have this file that we're referencing that gives you some helpers. Okay, so what the helpers do is, let's delete that and that. So what the helpers do with hash table is they check the limit, of each, and it gets an index and it checks the limit, and then just says, okay, so the supplied index needs to be a number. Okay, so that's how we're gonna, sort of use this hash table, is use numbers, and then, if it's not a number, then throw that error. And then all it's doing is saying, if this dot limit is less than or equal to the index getting passed to it, then we need to say the supplied index lies outside of the array's bounds. And what we mean by bounds is this limit right here. So when we do, we have a limit, and we're referencing that as this limit hits a limit that is greater than 3/4. Okay, it's going to actually give us a true. So this is simply just a true check capacity. Is just a function that's built to go through and check the size of the capacity, where we're at as far as like how many hashes, how many buckets we have in our hash table. Okay, so how many places we've taken up in our data structure. All right, so and then what that's going to do is then, if it gets to that size, we need to do something. We need to actually augment it. So every time that we need to resize this, or we should see, okay, so every time we insert, we need to check the size check the capacity. So if we're over 3/4, so if we're over 75% full, then we're going to call resize, and we're essentially going to double the size of our hash table. So it's going to take the limit, it's going to multiply it by 2, and then it's going to give us, I think we started at 8, so it's going to give us 16 total spots. So just to visualize that piece right there, the hash table and how they work, I'm going to draw it out. So let's imagine we have a hash table. Come on, give me my drawer. Oh, I probably did draw it, was just black. Okay, so here we go. So basically a hash table is sort of set up like, I mean, you can sort of think of it um, like a spreadsheet of sorts, but just kind of one column on the left and then one column on the right. 1, 2, 3, 4, 5, 6. And there's a limit to these columns. You know how you can do an infinite scroll in your, in like Excel? Like this is gonna allow you to only go to the limit that we set. And that limit is set to 8 at this point. So we should have, 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Okay, so now what's going to happen is you're going to have a hash function that sort of is a middleware between your code calling. So that hash function is going to take it in data and it's going to store that data. So let's say we had so data comes in as Ryan. We'll just do Rye. And then let's say that Nana comes in as data here. Whoops. And then let's say that Alan comes in as data as well. So let's say we called this 3 times with this data. Okay. Each one of these pieces is going to pass through our hash function. So this is our hash function, right? Okay. So our data, Ryan's going to come in and it's going to pass through that hash function and it's going to basically get a key and a value, and that key is going to be stored, as some sort of hash in here. So let's say the first value that comes in, gets hashed to a set of numbers. So Ryan is going to be placed here, and it's going to have a key assigned to Ryan as maybe, it should just be 1, 2, 3, A, B, C, whatever. So that's going to exist on the key. So now we have like an easy lookup for Ryan. We can easily track where Ryan goes. And so now we know the hash right here represents the data at that hash. Same thing for Nana. Now let's say he gets, whatever. So 5, 2, 1, XYZ, whatever. That'd be a really easy hash, and Nana is going to be stored here. Okay, and then the same thing with Alan is going to come through our hash function. It's going to provide a key, right? Some sort of hashed key, and then it's going to be the value at that hashed key. Alrighty, so now we have 8 as our limit for this hash table. And since 8 is our limit, when we get to 3/4 full, when we get to 75% of 8, we need to actually double in size. And that's where this idea of the extra credit came in with the collisions and whatnot. So as soon as you get to what would be the 6th item in this box, in this table, right? So let's say we have filled this all the way to here. Now we've hit 3/4, and so the next one that comes in is going to bump this to 16. So we're no longer going to have 8 places here. We're going to have 16. So then what needs to happen, we give it a new, so we create like this new, that's what's happening right here. So this dot storage, then we call new limit array, right? So our new limited array gets called, and then we pass it in that new limit because limit's going to be more than 2. So we basically have like this way to resize this hash table if it gets too big. And the power of that is that you basically have less, because each time you create a bucket or like an empty bucket in here, it's going to take up memory, whether that be in a database or on a computer somewhere. So let's say you don't want you want a finite list of memory based on how many users are in your company. What if you had like an admin portal and you had a hash table for every single user in your company, and you were a young startup, so you only had like 4 people in your company? You don't want this huge giant list, that could be potentially, you want to just maintain it to a small list, and it's going to be really, really small. And then you can, sort of use each bucket as like its own like object, right? So it can be, contains much more information about Ryan. Same thing with Nana. So that's a real world like example of what hash tables are going to be, sort of do like, and you can sort of think of them like objects in that they get a key value pair that is stringified. So in object creation in JavaScript, I'm going to delete this. and move forward. So if we create like an object and say const my object equals, you know, Ryan as that value, let's just say name and Ryan. Okay, and let's just log out my object. The literal representation of this, you know, would have this mapping pair, so like a key value pair, right? So just know that when this actually would like print out in any significant way, name would have quotes around it because that's how it gets stored. When it gets down to the nitty gritty and, you know, storing in memory, it's storing this way. So you can sort of think about hash tables in this same regard. Now, if I say my object dot age equals, I wish, you know, and now I log out my object again, you can see, you know, this is sort of kind of starting to look like, you know, some sort of hash table, but they, but it's like, so if I, you know, now I want to reference in memory, but this is specific to me, so it's kind of a weird example. So if I say dot name, you know, it'd say Ryan, you know, dot age, you know, so we're calling object, finding the reference. So that's kind of what would happen with the hash table. You say, find at this key what that value equals, okay? So the same thing we were doing. So, okay. So that's, we're gonna keep this check capacity function that goes and make sure our limit is stretched, you know, and our, you know, we can actually resize beyond that limit. Okay, so who has, so far, what kind of questions or what's super unclear, unfamiliar with hash tables? Is that pretty clear as far as like what the behavior is for, you know, capacity and, you know, resizing the limit of hash tables? So we're going to get into what happens next once we move forward. I just want to make sure that's clear. So if anyone asks you about the behavior of hash tables, you can at least tell them, oh, I know that there's sort of key value pair mappings. The key gets passed through a hash function and then set as a property on the hash table, or as a property, and then the value that comes through there, you know, gets assigned that hash. Okay, so that same way, and I'm going to give you a picture from the book just to show you exactly what I'm referencing. Okay, I'll just paste that right into Slack for you. Yes, I'm talking about extra credit in this. So I figured I'd give you the full shebang with hash tables as much as I possibly can. So yes, I'm going over kind of collisions and what happens with extra credit there. Okay, so, okay, now we have this insert function, okay? So the insert function, if we look, so that's the hash table helpers. Look at our insert. Our tests, sorry, that's what I'm looking for. Okay. All right, so should have insert, remove, and retrieve. Those were the basic ideas for this, and then the other tests were just to sort of handle the resize, and then should handle collisions properly. And we'll talk about collisions more in just a second. So right here we have a function called getBelowMax. All right, so that's going to basically sort of create our hash for us on the fly. So, and we want to make sure that we're sort of keeping track of this hash so that they're unique to each key that goes in. So, so when you get into other languages, I know that other languages use hashes and maps and things to sort of store their data. This or a slice, like in Golang, there's a slice data structure that's similar to like the array in JavaScript, but it has nothing to do with the array.slice, right? So that's sort of what we're kind of all mimicking with this data structure, but it just does a little bit more than that. So, all right, let's look at. So that's the helpers. That's our limit array that sort of gives us the limit in the sort of expands our. So the limit array class actually expands it's a class that allows us to expand the storage and the limit as we, you know, continue to add things more to it. So that's why it's there. So this dot storage equals new limited array. We pass, you know, this dot limit into it, and as that gets bigger, we can expand it. So that's part of the extra credit there. But then this get index below max is what's actually causing our hash to happen. So let me see. Okay, so index, we're going to go and we're going to call our check capacity function, And if it returns true, then we need to resize the table. We need to resize the hash table. So if it's 7 indices out of 8, that's above the threshold, and it's going to double in size. Okay, so it's going to go and it's going to work off of the resize function, which creates a new limited array, and assigns it to our new storage so that we get more and more. So it's kind of a weird thing to conceptualize here, that we have a class called our hash table, and then we have a class called limited array that's handling the growth and the resize of our storage that exists on the hash table. So just know that's kind of what's going on under the hood. And that's why this is hard to visualize in like a text editor or inside of Chrome, because we'd have to like paste all of this stuff over. Okay, so insert, we're going to take a key and a value. If the capacity is there, then we're going to, if that doesn't return true, then we're good, and we're going to move on. And we're just going to say our index is going to be get index below map, and ensure that our key is set to a string, and then we understand our limit that comes in. So let's look at our helper. We have a string and then our max. Okay, and so our max is going to be based on that limit. Okay, so then we're going to loop through the amount of length in the string, and then we're going to say, okay, so this is a little bit tricky to understand, so I'm not going to confuse you guys with this line here. Just know that what this is actually going to do is it's going to create a hash based on that limit given, and then it's going to divide that hash by the max that comes in. Okay, so that way we get some characters that we can use to create our key that exists on that hash table. So that photo that I put in Slack, that I'm actually going to show for recording purposes right now. So this is so picture your hash function, at your data coming through here. So the key that comes through here is going to sort of get assigned a value at each hash. So at each specific index, index meaning the letter in dir, let's say it's dir there, it's going to get 68 plus 17 plus 114 plus 114, because that's RR, right? So each one of these numbers represents that letter, that string that comes in. So that's how a hash works and operates. So now we can add them all together and say that that's our common hash, but we divide it by the limit and give it that index spot. So when it comes in at the end of this, we just say we want the math.absolute value of the modulus. Where is that at? Oh, that was down here. Math.index value of the modulus hash, modulus max. That's pretty, so I want you to go through this video over and over again to sort of like walk through that piece and just really kind of study up on what hash functions are doing, because it's going to take you 3, 4, 5, 6 times of looking at an explanation of a hash function, and for it to start to sink in. At least it did for me. But just know that this is a commonly written algorithm that's out there in the world, that if you need to use a hash function for whatever reason, you can just you borrow where that's written. So now we call that, and then so we assign that to our index. That's where it's going to be assigned as the index in the value, and then we create a bucket to store inside, and that bucket is, dang, I just exited out of that book. That bucket was the spreadsheet mapping, so the key value pair. So our bucket looks, sort of like this. Whole thing is our bucket, where our hash belongs in here, and that's our key. And then our value of Ryan belongs in here, and that's our value, right? So that's going to be one whole bucket. So that's what we're saying here. And then we're going to say wherever we're at, get the storage's index. So we're going to say this.storage.get index, and we're going to put that, we're going to assign this new index that came out of our index below max hash function, and put that bucket into the storage. And then now if we're going to say, okay, so now if this is, if that is undefined, then we're going to set it there. So we're going to assign bucket to the storage.get index. So we're going to see, if that's defined. If it isn't defined, then we're going to set the first one there. Okay, and you can see now that index is our hash, and then we have our key value associated array. So how this looks in code land is going to be, here's our hash table, here's our hash, right? And then inside of here is going to be an associated array where in that array it's got this tuple in here, and it just says the hash itself. Okay, so under the hood, this is kind of going to be what it looks like. Okay, and then the value on that place. Okay, so that's a better representation now of a full-on bucket. So that's kind of what's going on there. Questions if you got them? Okay, so the cool thing about hash tables is insert is super duper fast because it's going to just check that index length, it's going to check the array, it's going to just be able to just go to the right spot and put it there. And your stuff is super duper organized as well. So then, yeah, so now we just need to loop through it and set the item in the next available bucket in that array, okay, or in that hash table. And then removing is very similar. So we check our index, we pass it, we give it a key. This time we don't need a value because we're just looking for the key. And then we're going to say, if we find the key, then we're going to splice it out of the actual hash table. And this is all doing the same exact thing as this line, these lines above. It's basically figuring out what the size of our hash table is. It's going to loop through it. Eventually, it's going to find the bucket, create that bucket, and figure out where it's at. And then if it is one, then we're just going to say return. Or no, we're going to change our storage. We're going to change our hash table and set the new index on, and then set that value to actual undefined. So those helpers, if you want to look at those getters and setters, they're right here. So we have the get index, and then we have the get length, okay? And then the setter should be on there right here as well. So we created that setter and the getter for you, and then this length just returns the storage.length so that if it knows the storage's length is 3/4 full, it's going to handle the resize stuff. Okay, and then yes, so retrieve. Now we need to make sure that we can get into our storage, our hash table, and retrieve a bucket based on the key given. Okay, so very much similar to looping over an array and saying, if that array's item equals this, then return the bucket itself wherever we want the value out of there, so we can retrieve the value. So that way, if key comes in, we have our hashed key. Let's say it's cool. Let's do this. I love this annotator, by the way. So we have our bucket, right? And we have our hashed value, whatever it's going to be right here, our hash, okay? And so our key comes in, that's what our hash is, right? And then it's going to just basically say, because remember we had that tuple here, so it's sort of a nested array, but it's just an associated array, so there's a key, essentially, it sort of behaves like an object, right? And then a value. So that's why we return the bucket at whatever index we find where the key is the same, and then we return. So if bucket at I at 0, it equals this, if this key equals this hash here, then we're going to return the value out of it, and that's the retrieve function. Okay, so that's exactly what this is doing. Okay, so that is a very high-level crash course on hash tables, and even linked lists is a little bit high level as well. I highly recommend when you have some time to go back and reflect and think about these things and just study up on them, and move forward from there. As you continue to learn this stuff, it's going to become more and more familiar to you, but it takes time. It's not something. So this is stuff that they teach in computer science degrees, where it actually takes, you know, semesters of work to figure out and kind of learn. If it's just clicking for you, that's awesome, because, you know, it makes sense in whatever way that you've been able to study it. But yes, for me, it did not click the first time that I saw it, and I'm still like learning as I'm going. So I'm still kind of sitting here and learning stuff with you guys, and sort of looking at this code and just dissecting it piece by piece, and really trying to get the high level understanding of this stuff so I can deeper understand it, you know, and, you know, get further and further into computer science topics. But now, so what's going to happen is I'm going to save our video.